Great. Yeah, so chapter 17 and the part 2. So at the first part, like on the previous call, we have talked about subsections 1 through 4, and basically they were about like the notions of the space-time in the past, like about Aristotelian physics or Galilean relativity, and also Newtonian laws, etc. Basically, the story was going on like in this way, like Aristotelian space-time. I will call it, for example, A here. It was something like just a direct product for space, so it was like R3 over the R. And afterwards, if you move to the Galileo, like to the G thing, plus some Newtonian laws, like an L, you will have, you kind of should move from the absolute space to the relative space, and therefore you will obtain something like a fiber bundle there. So it will be fiber bundle over R with the fiber R3. So it's like, don't remember how to say this. Okay. Anyway, so it's fiber bundle over R, and basically the inertial motions there, they were kind of defined using the connection, and connection, but it's kind of the really simple connection. So torsion and curvature here is 0. So we had some kind of the connection here with 0 torsion and 0 curvature. And afterwards we went on and kind of jumped into the principle of equivalence. And this principle of equivalence kind of stated that actually the inertial motions should be defined in a free fall frames, and therefore kind of we cannot differentiate between the gravity effects and the acceleration effects. And that was the insight of the Einstein. And basically today we are starting with kind of modifying this Galilean space-time and including this principle of the equivalence into it. And probably I can actually kind of continue here and just talk a little bit more, like provide you with abstract, how to say, like the view from the above of the whole chapter. So basically the plan today is to include this principle of equivalence into this Galilean bundle, and basically obtain this kind of N bundle called Newton-Cartan spacetime in the book. And the main difference with this bundle will be non-zero curvature here. So basically this like bundle, the manifold, four manifold of that bundle will have the connection with non-zero curvature, and basically it's kind of packing the gravity into it, something like that. So I think that like when you are moving from the inertial motions, where you call the inertial motion something where the sum of all non-gravity forces equals 0, then you should kind of pack gravity somewhere, and that gravity packing goes right into the curvature, and curvature here will be like non-zero. And in the chapter we will see the two examples of this curvature having kind of gravitational effects on the particles, like the Weyl curvature and Ricci curvature. And afterwards we will go we'll continue and talk about the speed of light limitations and basically the problems, speed of light, problems it kind of arise, or how to say this, like the problems connected with it. I mean, with merging this speed of light constancy with the relativity frames. And we will talk about some kind of the space where, so we will have like a row for manifold, and we will try to give it some structure to incorporate this speed of light limitation into it. And basically we will arrive to some kind of the space called like Minkowski space. And basically it will have like also zero curvature there, something like that. I don't remember exactly, but like just from the tip of my mind, we'll have something like a flat Minkowskian space there with curvature 0, and afterwards we will kind of merge it with the previous ideas and obtain like Einsteinian space with non-zero curvature, and the whole process there will be really similar to the process we had with the Galileo and Newton-Cartan bundles. Yes, so anyway, let's go to the material and just start off there. Do you see book nicely, or maybe I should zoom in? Just say if something wrong here.
Maybe zoom in a little.
Okay.
Looks good.
Hi.
One moment. Better?
Yeah, that's okay.
Yeah, so basically we have talked about the 17.5 previously, actually, and I have spoke already about the basic idea here. So it was like the work of the Henri Cartan, famous mathematician, and the work was done after the Einstein theories were developed. So it kind of run in terms of chronology. But anyways, anyway, it kind of the modification of the Newtonian space-time and giving it a structure more similar to the general relativity structures. Yeah, and basically it's like the same manifold we had previously, like this Galilean bundle manifold, but with non-flat curvature there. And yeah, I'm not sure about this picture. Maybe someone can make some like some input here. So as far as I understand, then we have like the same structure, and on the left here we have this Newton-Cartan bundle, and here we have this Galilean bundle. And basically Penrose talks that structures are essentially equivalent to the previous like G bundle, and it can be seen by sliding the fibers and kind of straightening out the world lines of the particles there. Here I'm not sure what does it mean like in the rigorous and more like strict mathematical terms, and probably like we cannot just remove the curvature, right, because the gravity is there, but probably he just says like is saying here that we kind of can move from the picture where inertial motions are depicted where like sum of all forces equals to 0, to the picture where sum of all non-gravity forces equals to 0, where gravity is encoded into this kind of curved world lines there. So like the only straight lines there will be like free-falling reference frames. Yeah. Okay. So.
Yeah, I think the important piece is that saying like the absolute strength of the gravitational field is not what's important. It's about the change, which is why if we have a case where we have a constant field, that's the same as having zero field. You can just shift to this other view, and you get the same physics.
Yeah, and that's kind of the next thing to talk. So basically, where he's saying about this here, probably that's here, like gravitational field that is completely constant, right? Like both in magnitude and direction over the whole space, but perhaps varying in time. We can kind of compensate it, right? Just by changing our like coordinates, something like that.
Yeah, I think that's part of the point that you don't have any absolute coordinates, so that's why you can shift the planes like this, and they will retain their relative relation.
Yeah, and probably I had somewhere the question about those, but I'm not sure. Okay, so he says here that most gravitational fields count as essentially different from the absence of gravitational field. And probably he's talking about like some kind of the non-global gravitational fields, some kind of the local gravitational fields, right? Because when you have some kind of the gravitational curvature locally somewhere, then probably you'll be able to remove it only locally, and you will not be able to remove it in terms of the whole bundle. But it's kind of still a bit misty material for me, so I don't grasp it. Okay, anyway, here he talks about the connection for our manifold N, and he says that the geodesics of this connection are to be straight world lines that represent inertial motions in the Einsteinian sense, and this connection is torsion-free, the same as in the Galilean case, but it will generally possess curvature, and the presence of this curvature is the exact thing which makes some gravitational fields essentially different from the absence of gravitational field. In constant with the especially constant field just considered. So basically, that's like his point probably about the global gravitational effects can be kind of removed if they are over the whole space with the same magnitude and the direction. But if they kind of are different in different localities, then you kind of should consider it using this curvature. That's how I understand it. Yeah, and afterwards he goes to the examples actually, and basically the two examples he gives us here is about the Albert, the astronaut here, and he kind of looks at the sphere of the particles around him and takes some big object like Earth or some other planet here. So, for example, Albert could be in the orbit and just under the free fall here. And due to this planet gravitational field, this sphere of the particles around him will kind of deform into ellipsoidal shape, and the volume of it will be preserved initially. Yeah, and basically that's the same thing Moon is doing over the Earth, and why we have the tidal forces. So you kind of can imagine the Earth here instead of Albert and Moon here, and you obtain the same effect. Yeah, and in more rigorous terms, this curvature could be called Weyl curvature. But anyway, let's take a look this second example also. So this second example is when we considering a sphere of particles which are located over some like big lump of matter, like a planet here also. And if you take it into the consideration, the gravity will kind of just shrink it down uniformly, just shrinking the sphere. And in terms of the curvature of this like Newton-Cartan space-time, that will mean those two pictures. So basically we have like a two-dimensional spheres here, so just circles, and Albert is right at the center, and some particles will go inward, some particles will go like outwards. We'll obtain more ellipsoidal thing here, and the matter is kind of is outside of these like world lines or shapes here, right? And the Ricci curvature displayed on the right here have the mass inside, and basically we have those circles shrinking to like smaller ones at the end. Yeah, one moment, I just will go through the my notes just not to forget anything. Yeah, so in generally both effects could be present, so like both curvatures could act together there. Yeah, and in fact, Cartan showed that it's possible to reformulate Newton's gravitational theory completely in terms of the mathematical conditions on the connection. Yeah, and those equations were about the curvature actually, and Penrose not giving us like a detailed description of this Cartan theory, but he's saying that this theory will be really important for us for like considering later, maybe while talking about some kind of the other theories or maybe cosmology, when we will need some kind of the limiting procedure done on these theories to go from like from relativity theory of the Einstein to the Newton and back and something like that. So basically that idea, like Cartan scheme, is not needed to understand the Einstein general theory of relativity, but it will be needed to for more profound themes in the theoretical physics later. Yeah. So, any questions? Maybe you have something to ask about this, or maybe to add. Okay, so we are moving now to the speed of light questions and the subsection number 6. So, and at the beginning of this chapter, Penrose talks that about to go from the Newtonian picture of the world to the Einstein's picture, you kind of need to apply 3 things, and it's like principle of relativity. It was there, okay. So we need to add there also to the principle of relativity, principle of equivalence. And also the third component is the limit on the speed of light, or like the finiteness of the speed of light. And actually it's remarkable that historically all 3 of these basic ingredients can be traced back to Galileo. So he kind of had a chance to kind of grasp or to feel everything of those 3 ingredients at his times, but it kind of needed more profound tools and powerful mathematics to be kind of joined together. Yeah, so both Galileo and Newton, they kind of have had powerful suspicions considering the deep role of the nature of light with the forces that kind of bind matter together. Yeah, but actually those, like combining those things needed something more, and one of these things was electromagnetic theory, which was developed by Faraday and Maxwell in the 19th century. And we will talk about this theory later, but the key ingredient we need now is that the consequence of this theory is that the speed of light has a definite fixed value, and it equals 3 by 10 to the power 8 meters per second. Yeah, and if we assume that the speed of light is finite, then basically we will have the contradiction with the relativity principle, because if you take like that will mean that like the light is independent from the source velocity. So it's kind of counterintuitive for us living in the world of the like small velocities, that if you will travel like in the neighboring reference frame to the light with some other speed, then the speed will not add to the speed of light, and the light will remain the same. And basically Newton and Galileo was thinking about light and the speed of light, but they have thought about light more in terms of the particles, and thereby they were thinking in terms of the dependency upon the velocity of the source of the light. Anyway, the observations of the distant double stars showed that light speed is actually independent of that of its source, and it was kind of experimental approval of the Maxwell's theory. And in Maxwell theory, the light takes the form of the waves and not particles, and therefore we kind of need to modify the notion of the space-time somehow to include these condition into it. And therefore we will need this new tool called the light cone. And basically we shall start here with a blank state, or rather with a featureless real four-manifold, and we wanted to see like what does it mean in terms of the geometry of it to have like some kind of the fundamental speed which cannot be beaten. Basically we can kind of assume that we are looking at the photon or photon, yeah, right. So it's kind of the particle of the light, small like light packet, and we can imagine like all different rays of light that goes from some that pass through some point P in all the different spatial locations at the point P of the space-time. And in the like space-time terms, as we see on this figure, the light will go and just like spread in the space in the concentric spheres, something like that. But if you take into the account the time element here, then basically you will need to use the conic structures here. And why is that should be done this way? Basically because like this diagonal here, it kind of symbolizes that maximum, like the maximal velocity of the light is finite, and therefore the light could not escape some cone here. So the trick between those two pictures is actually suppressing one space dimension here, so obtaining concentric circles, which you see as the like slices of the cone on the picture B here. And basically light which will go up, it's kind of the light which go to the future, and light which is down here, the down cone, it's the light which kind of could come on the point P from the past. And the point, one moment. Yeah, and basically Penrose says that because we are talking about velocities here, we are basically talking about the tangent vectors. And therefore, we should consider those on our manifold, those cones should be in the tangent spaces. So basically, the tangent space should have some structure providing us with these light cones. Yeah, and actually he says that usually he uses the term null cone here, and the light cone is reserved for the actual like locus, like a set of points in space-time that is swept out by the light rays passing through a point P. Yeah, so he kinda calls at like the cone at the point P of the manifold, so we kinda go into the tangent space, have some kind of the null cone at that point there, and it will look like this. So the word line of every particle should be inside this cone, because kind of the particle is kind of cached inside of it, because the particle is not allowed to exceed the speed of light and going out of this barrier limited by the cone picture. So basically, to have this cone, we kind of will need to introduce the matrix here, and that matrix should be should have like special should have special signature called Lorenzen Signature, so it will or like 1-3 signature, and basically that will mean that we will have like 3 positive and 1 negative, or 1 positive and 3 negative terms there, and he says here that by referring to an instant, I really mean that these considerations are to apply to the infinitesimal temporal neighborhood of P. So probably I think that he's talking about this, like why that cone is called the null cone, because the matrix on it like will be equal to 0. So for the like word lines or velocities which are equal to the like speed of light velocities, we will obtain this cone exactly, and therefore the value, like the value of the metric on those, will be equal to 0. Okay, I think we can skip this. And he also talks about that, like, because we have this constant speed of light, all null cones are parallel, and therefore we will obtain something like this picture here. So we kind of obtaining this Minkowski space, and it's flat, and at every point of it, its null cones are uniformly arranged. And as far as I understand, he's not talking here about the whole tangent space. He talks about the whole manifold here. Do you agree with me? Because I'm not sure about this, but it seems to me that that's the exact picture, because like in every tangent space, you kind of have this velocity space, and therefore we will have only like 1 zero cone in every like Lorenzen space tangential to our space-time here.
I usually like to think about this stuff in terms of like causality. So for the null cone, it's talking about like all events that are spaced in a way such that light would travel from like that distance or it would travel that full distance within that amount of time. So what the null cone really says in terms of like causality is that a signal would have just enough time to get between the two events. Whereas, like, if you had a time-like cone, then there could have been a causal signal that could influence the two events. The null cone is where there's just enough time for light to have gone between the two events.
Yeah, and that's like exactly a theme for the next subsection, actually, about the abandonment of absolute time. And basically, when we are considering our like Galilean spacetime G, we want to have the addition to it in terms of the cones. But like, can we include the notion of the absolute space-time into our picture? That's the question. And this kind of will not be possible to us, actually. Yeah, and here Penrose talks about some kind of the, like, if we have had this like absolute time thing and the bundle structure, then for our Minkowskian like cones, we kind of could have defined like a special or preferred state of rest at each event, and therefore we kind of we lost the relativity principle. I also not sure like what he means by this exactly. Yeah, but anyway, if we'll go further, he talks about this in that way, like this argument is simply expressing the common sense notion that if there is an absolute light speed, then there is a preferred state of rest with respect to which this speed appears to be the same in all directions. What is less obvious is that this conflict arises only if we try to retain the notion of an absolute time. Maybe someone can also do some input on this quote. Oh, sorry.
So sorry, what's your question, Slava?
My question is about, like, if we are taking the notion of the absolute time into the account and the speed of light like also, then why do we have this sorry, preferred state of rest? So what does he mean here about like this preferred state of rest here, with respect to which this like the speed of light appears to be the same in all directions?
So you could think about being on like on a spaceship or something, and you're traveling like really fast, like close to the speed of light. The error comes when you try to like shine a flashlight, in the direction that you're moving, because like in Galilean relativity, or just like like the relativity of like other wave signals like sound or pressure or something, then the waves would be compressed if you were to emit them forward, and they would be extended if you emit them behind you. But if you were to assert that there is an absolute time, then let me think here for a second.
I think I got the basic argument. So basically, if you have something like a particle moving with some velocity, right, and you have some kind of the distance which the particle should like come across, something like that. And
Really quick, what's absolute time in the book? Does it mean like a fixed like speed limit, pretty much, or was it something else? I tuned out for a second.
Absolute time is actually like
I haven't had that chat
Single
before.
timeline for all the universe.
yeah.
Yeah, it's
Like
saying,
the time
like,
time
independent-
flows in the same rate everywhere.
Okay, well, yeah, this I think I can explain it if like after you've done what you're doing.
So just basically, if you have some kind of distance here, like d, and particle moving with some velocity v, then we can kind of just divide like d by v and obtain d time, right? And if we will have some limitation on the velocity, like for the speed of light here, and if we should consider that if that's a photon and it travels with near light speeds, then for this speed to be fixed, we cannot like fix this time here. So as far as I understand, you kind of need to like shrink time to compensate the velocity for the like flashlight on that spaceship the Joe talked about.
Yeah, exactly. You know, this example, it's also, you know, I think a really good way to think about relativity is the way that Einstein did with trains. So, you know, perhaps it's better not to just have one source of light, but two sources of light at either end of the ship. You know, so like one light at the front of the ship and one light at the back of the ship.
Why not just use the train metaphor? I think your analogy will be a lot easier if you just use the train thing, like two separate sources of light in a spaceship. It's just kind of funny, like two flashlights. But
in the train example, you ignore the tracks anyway, so it is the same as the spaceship. But
it is the same. It's just you know.
So you have a train coming into the station, and at the moment that the center of the train passes the platform, you know, the front and the back lights on the train flash. So if you're on the train, those two signals reach you at the same time. But if you're standing on the platform, the signal that is, you know, receding away from you takes longer than the signal that is coming towards you.
I think it's the other way around. If you're not on the train, I believe it's. Wait. Did you say that the lights were at the ends of the train or separate from the train?
Well, so yeah, now we're kind of moving towards simultaneity stuff.
I may have just misheard what you said. Did you say that the lights were on the train?
Yes.
Then you're right. Yeah. Okay. Sorry.
Yeah. So I'm saying the lights on the train flash at the moment that the center of the train passes the center of the platform.
Yeah.
And if that's the case, then for someone standing on the train, they'll receive the light signals at the same time. However, someone that's standing on the platform, you know, one light will be moving toward them and one light will be moving away from them. So there will actually be a difference in time that he receives those two light signals. Yeah, this is the right picture.
Yeah, so it's kind of the train wagon, and if you have some kind of platform here and some person standing down there, but probably he should stand like right here to the center, right? And he will also see those lights, right?
Yeah, so the person on the train will see the lights simultaneously because they're equidistant and they were sent off at the same time.
They're in the same reference frame.
Yeah, and then the person on the platform, you know, because this train is moving very fast, the signal at the front of the train is moving away from him, and the signal at the back of the train is moving toward him.
Yeah.
So because of this, there's going to be a discrepancy between like the difference of time when each observer receives a signal.
Basically, he will receive this signal faster because train moves there.
Just out of curiosity, what chapter are you on in Road to Reality?
17.
Thanks.
Yeah, you can see this here, like on the video, in the screen share. Okay.
Sounds like he's driving. He probably can't.
Oh, okay.
That's probably why.
Anyway.
So does this answer your question, Slava? Is it like, because this really exemplifies like why if the two observers had their clocks synchronized, then you would have some sort of a conundrum where one of them receives the signals at the same time and the other receives the signals at different times. Mm-hmm. So if their clocks were synchronized, they wouldn't be able to reconcile the two.
Yeah, and therefore, like, the time is relative here. Okay, so basically the idea now is to abandon this notion and actually go away from this like bundle-like structure of the Galilean relativity, because we kind of are not able now to have this like base space, the timeline, and therefore like by having this no absolute time, no absolute space picture, we should have just like some kind of the four manifold with the curvature there and also light cones. Yeah, and at the bottom of this page, Penrose talks about like why absolute time is so intuitive for us, and he says that the only reason for having an absolute time so firmly ingrained in our thinking is that the speed of light is so extraordinarily large by the standards of the speeds familiar to us. So he kind of tries to draw like a real light cone, and like in reality, like in a non-normalized situation, which is more easy to draw, the light cone will look something like that. So it will be like really white one, and therefore we, as the creatures living in the low velocity world, we just kind of not able to kind of escape or approach this like wall of the light, real light cone, and therefore like real life experience tells us that time is absolute. But like this experiment with train, thought experiment, they kind of destroyed the idea of the absolute time. Yeah, and afterwards he talks about the renormalization. Like in most theories today, we can just kind of renormalize everything and take our speed of light to be equal to 1, and therefore for the distances we should use like the other notions, for example light seconds, which are obtained from the from the like 1 second multiplied by the speed of light. So actually that's the distance which the light will travel in 1 second, or light year, it's a distance which the light will travel in 1 year. Yeah, so something like that.
I'm gonna have to disappear, guys. I've got some homework I didn't realize I had. You call what you're up to. Keep it up.
Okay. Okay.
Thanks for joining us.
Thank you.
Yeah. I hope to join next time. I'll talk then. Peace.
Yeah, welcome. Okay. Great.
So Slava, I think there's one more thing that I wanted to point out, which is so in our low velocity world, there's actually no paradox. Sorry about that. There's no paradox for like sound waves where there's like variable speed of sound. The paradox comes in when you're asserting that the speed of light is a constant, because like, you know, if you draw the same picture with the trains, and rather than a light signal, it's like a sound.
Mm-hmm.
And if you're moving close to the speed of sound, the discrepancy is not due to absolute time. It's due to the variable speed of sound. It's that sound adds in the way that Galileo thought, but light does not. So like the main conceptual difference is the absolute speed as well. Like what I'm pointing out is that the necessity to abandon absolute time comes from the assertion that the speed of light is a constant.
And that also could be reformulated in terms of the dependence on the speed of the source, right? Then.
Right.
So the speed of sound will depend on the speed of its source.
Exactly, and that's actually, you know, pretty fundamentally, that's due to the medium in which the waves are traveling in. You know, the sound waves are traveling through air. You know, they're actually pressure waves within the air molecules. However, the medium in which light travels is actually not like a material like we think of for other waves. You know, the medium is just space-time. It travels through vacuum, whereas sound could not.
Yeah, interesting. And actually, as far as I remember it, like the speed of light, it changes in water, or no? I don't. It seems that that's true. Like
Yes, it slows down. That's what I have.
Well, so yeah, the interesting thing is that it does change in water, but it changes in water in a weird way. So the way that it actually changes is that it has many different scattering events with the water.
So it's the refractive index, kind of the angle, like.
Yeah, so you can think about like the water as actually being like obstacles to the light, whereas like in between each obstacle, it still travels at c. But there are many obstacles, so it's bouncing around, and in order to pass through the full material, it has to actually travel a further distance.
I also recalled that those scattering things with light is actually like implying the color of the sky. Like the blue color is like a scattering effect.
Absolutely. Really scattering.
And that's why, like at the sunset or like when sun rises up, the light is more like a reddish one or orange.
Yeah, and that's related to the average spacing of the air molecules.
Like because we will have like a much bigger amount of the air when sun sets down, right?
Yeah, and so the air molecules are spaced out, I believe, about on the order of blue light. So,
well, okay, I got it. I think that the reason that sunsets are red and the sky is blue is less about the amount of air and more about the angle. Blue is scattered at a higher angle. So a sunset is red because all the blue light is scattered away. But when you look at the sky, not at the sun, it looks blue because that light has to scatter off of air molecules at a sharp angle.
Interesting, yeah.
Yeah, so that's a great intuition there. I think, yeah, just to kind of conclude what I was saying about like the difference between the light and the sound waves is that because the light is traveling in vacuum, the reason that it takes longer to travel the same distance in water or air or something is really is not because it's traveling a different speed. It's because there's actually more scattering events.
So it's kind of it kind of takes elongated paths there, right? Something like that.
Yeah, it's like the straight line path is not smooth.
Yeah. So it's kind of like a Brownian motion, something like this, like really curved thing. But I'm not sure like about the real trajectory, of course. Okay, so should we continue now?
Sounds good.
Great.
It would be good if we can finish on time. I'm gonna attend the Epsilon group in 1 hour. But thank you.
Yeah, of course. It's kind of, we almost finished with the material. It's like two pages. So.
Yeah, great.
Almost
Sure, we will have some
here.
discussion afterwards also.
Yeah, I'm also planning to attend a bit, just take a small glance of the Epsilon group today. But anyway, let's continue and discuss further. Okay, so basically here Penrose was talking about the history of the space-time and actually the amount of work done by the Hermann Minkowski. And he is exactly the man who coined this quote that like space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. So basically we kind of come back or kind of create like the new geometrical reality here, with like kind of forgetting these bundle structures and products and just going to some kind of the like curved manifold and using that for the space-time. Yeah, and at the end of this subsection, Penrose talks more about the like Minkowskian space-time, and he's talking that we kind of must fix some kind of scaling for the matrix that provides a measure of length along word lines. Okay. I'm not sure what he scales here. So he been talking about the scaling scene at the end of the 17.7. But anyway, basically he talks that the matrix will measure for us the time measured by an ideal clock, like situated at our like word line or point traveling through the space-time. Yeah, he kind of just writes this formula here, and basically with this signature you will obtain exactly like something like this, like t squared minus x squared minus y squared minus z squared, something like that, and it will be equal to this thing here, like our modified Pythagorean theorem, and you'll kind of take the square root of this and take the integral of from a to b, where a and b like 2 points in space-time, and it will have like d, probably like ds probably.
So the way that you get there, so that all of these variables that you have in the square root, they would have like a d, because they're actually like total differentials.
So it will be, you mean it will be like this? I said that I should add it like in this way, or what?
Yeah, exactly. So So that's the way that you do it, but this is a hard integral to evaluate because you have like a square root of a bunch of differentials.
Yeah, sounds hard.
So what you could do to get around this, there's something called the proper time, d tau. And you can multiply this integrand by d tau over d tau. So what you'd end up with is each one of these terms would be like dt squared, d tau squared.
And you mean you'll have something like this here?
Yeah, on each one of the terms.
So you kind of divide everything and multiply here also by d tau.
Yeah, that would just be d tau, not d tau squared outside the square root.
Yeah, it's just d tau.
My apologies. There would be squares when you bring it in the square root.
Yeah, but no.
Outside it would just. Yeah, so that's it. I think Penrose will get to this, but I was just pointing out that like in order to actually evaluate this integral, you need to parameterize it.
So this tau will be like a parameter over the space-time curve.
Yeah. So what its actual value is the proper time between events, meaning this metric times xa xb, it'll have only the time-like part. Like all the space-like parts would be 0. So the d tau is just saying it's like it's the value of the interval when the space-like parts are all 0. But we'll get to more of that in a little bit. But that is how you evaluate this integral.
Yeah, and actually I just wanted to say that like from this kind of metric where you have something like positive here and other things with different sign like this, for example, and if you take like the null of that matrix, you'll obtain exactly the cone structure, because after moving everything here, you'll obtain like this thing, and you will have like for every t parameter a circle of the radius t here, and that's exactly the cone structure you have seen. So it will be something like that. Yeah, and when Pedros talks about these signatures, he says that his preferred choice is to use plus and 3 minuses signature, because in this way, yeah, he will, I don't remember exactly, he will measure the time nicely, something like that. I don't remember where it is exactly in the text. But anyway, he talks about that in his way of talking about the space-time and the cones. He was more talking about the null cones structure of space-times, even more than its metric. And he says that the idea behind it is that the null cones are indeed more fundamental than the metric, and that's because they determine the causality properties of the space-time. Yeah, and basically he kind of demonstrates it here on the picture, where he shows that while particle is moving through the space-time, its world line should be inside the null cones everywhere at every point here. Yeah, and he says that this world line is called like a time-like curve, and if you will have the photon traveling with the speed of light here, then this interval, our matrix, will be equal to 0 exactly, and therefore it will be tangent to the null cones everywhere. So this world line will be called like space, sorry, not space-like, light-like. and basically if it will go off somewhere, then probably that's not a good word line, right? So it's not like not good from a physical viewpoint, because it kind of connects two events which could not be kind of traced or kind of connected with some kind of information or something like that. So we kind of cannot travel beyond those cones. Okay, so, and he also said here that no physical particle is permitted to have a space-like world line, so the one outside the associated light cones. And in the note at the end of chapter, he talks a bit about the tachyons, and they are like hypothetical particles which could like theoretically travel with faster than light speeds. I don't know anything about those, but it's kind of just cool notion, maybe interesting one, and maybe we will encounter that later. Okay, yeah, so basic idea here is that the light cones are providing the causal structure for the space-time, as Joe have already mentioned, actually. Yeah, and at the end of this subsection, he talks that relativity of the Galilean physics is actually like holds just as well as it does for the G bundle, because like every point of the Minkowski space is on equal footing, and he just says that not only every point is on equal footing, but also all possible velocities are also on equal footing with each other, and that this will be explained more in the next chapter, actually. Yeah, and at the end we kind of come to the final section about Einstein's general relativity. I don't remember. Let's take a look at this picture. So we have like light cone here. So it seems that this picture is actually about this subsection already. So it has some like curved cone here, but I'm not sure like totally. Okay, let's take a look at the text. So the main idea here is that we can now apply the same generalization to the Minkowski's space. We had like, and as far as I understand, that's the like four manifold with those Minkowski spaces at the tangential as tangential spaces for the velocities. And previously we had the procedure which was like moving from the Galileo's G bundle to the Newton-Cartan space-time. And basically the idea was in the introduction of the non-zero curvature for our connection, and that's exactly the idea for like forming the Einstein space-time from the Minkowskian. So basically the Minkowskian space is kind of flat, and that's why I kind of marked here that it kind of has the zero curvature. So R here is not a real space, it's just a curvature, and it's kind of flat space, flat for manifold in some ways. In terms of curvature. And basically in an Einstein case you kind of introduce those curvature things like Weyl and Ricci curvatures, as far as I understand, yeah, let's read a bit about this. So the differences are slight, but things can get decidedly more elaborate when we examine the global causality structure of a complicated Einstein spacetime. And probably he will talk here about like we can come to some things like causality violations here, but let's take a look at the picture 17 at first. So Einsteinian spacetime of general relativity is depicted like this here, and this is generalization of Minkowski space, similar to the passage from G to N, and it just has like the Lorenzen pseudometric G, which defines the physical measure of time here, and nothing about curvature. Okay, strange. I hope that he will mention something about curvature there. Anyway, he's talking about that like the causality structure of our this epsilon, or I don't know what, like E manifold, is determined by the matrix G, and extreme like unphysical situations with closed time-like curves might hypothetically arise, and he kind of shows us some word-line trajectory going into circle in the space-time, which is like acceptable physically. So it's time-like inside every null cone there, and that's like called causality violation problem. And such situations are normally ruled out as unphysical. And his own position would certainly be to rule them out for a classically accepted space-time. Yet some physicists take a considerably more relaxed view of that matter, being prepared to admit the possibility of time travel, and such closed time-like curves would allow, they would allow such curves. He also talks a little bit about black holes here and some like exotic causality structures. Anyway, he says that we saw that like any good enough metric, as far as I remember, so it kind of should have some nice qualities, like determines a unique torsion-free connection for which connection over this, like applied to this metric, equals to 0, so it kind of preserves the metric while parallel transporting it. And this kind of applies here also. So basically we have this like Minkowskian manifold, as far as I understand, and we kind of introduce Levich-Vita connection on it by this equation, and that equation will kind of induce torsion-free connection, but I'm not sure how to set up the curvature, probably by kind of playing somehow with geodesics or something like that. So he talks here that the time-like geodesics of our connection and their like inertial motions are fixed by the properties that they are locally the curves that maximize what is called proper time. And this proper time is simply the length as measured along the word line. And it is what is measured by an ideal clock having that word line. So basically that was exactly thing measured here. So that's it, that's the proper time tau. And by choosing this matrix, Penrose or signature, Penrose kind of emphasized that we have the positive time here, and by kind of subtracting the distances from it, basically something like that, we kind of obtain the notion of the time here. And by choosing the wrong signature, like this one, we will obtain like negative time. Probably that's the reason why he prefers the plus and 3 minuses signature there. Okay, and the connection has a curvature tensor whose physical interpretation is basically just the same as was in the case of N, So like in the examples with the astronaut Albert, or like the Ricci curvature, when you have like concentric spheres. Yep, and the last paragraph here talks about like what locally distinguishes Minkowski's space of special relativity from the Einstein's space E of general relativity is that curvature equals to 0 for the Minkowski space. And actually in the next chapter we will explore this Minkowski special relativity spacetime. And in chapter 19 we will go and like in further or like richer details take a look at the Einstein's spacetime, basically. Yeah. So it seems that's all.
So why is G being referred to as a pseudometric? What is it that makes it not a metric?
It's pseudometric because it's kind of cannot be like positive definite metric because of like non-positive signatures here.
Oh, okay.
Yeah, so if you had like all pluses here, then yes, it could be like just a metric. But if you have like at less like one minus there, you will obtain what is called like pseudometric.
Okay, and my other question from this this section is, or this paragraph is right after this. It refers to it's drawing the difference between this metric and the one, or and when you have the Newtonian spacetime. Okay, it just says now G is not degenerate, and that's why the metric is completely determined by G, and you don't have to specify them separately. What in the, if we need to go back to the Newtonian section, what does it mean by G being degenerate?
Yeah, I'm not sure to what part you're referring, like in terms of this case, like somewhere here probably. So like why we can, I'm not sure that we are having, we have some kind of metric here. So in case of the Newtonian spacetime, I don't remember anything like about the metric. So in this case, we were talking more just in terms of some connection present, but like no definite metric here, because like this metric is introduced afterwards when we introduce the equation of the speed of light.
Okay, but the sentence that I'm looking at is, this is quite different from the situation with Cartan's Newtonian spacetime, where the connection had to be specified in addition to metric notions.
On what page is it?
Is
somewhere here, like 409? 409, right?
Yep.
Could you guide my finger like to bottom?
So yep, that paragraph down a little bit. Right in there.
It tells us that Einstein's concept of inertial motion is completely determined by the spacetime metric. This is quite different from the situation with Cartan's Newtonian spacetime, where the connection had to be specified in addition to the metric notions.
Yeah, and the next sentence saying that because G is not degenerate, the connection is completely determined by it. Now, I didn't know what it meant by that.
Yeah, he just meant this, like this theorem, only degenerate metric or non-degenerate metric kind of can produce this connection probably. So if you will go to the chapter 14.7, probably it will have this thin.
This was this was one of the problems in 14 was proving the uniqueness of the connection. And I think from that you can show that G is is non-degenerate.
I vaguely remember that. Mm-hmm.
Yeah, I just want to find like what does it mean to have like a degenerate matrix.
I think he means degenerate and non-degenerate.
Mm-hmm.
I think he means it in the way that like that physicists say it, where it's just like unique or not unique. You know, like for example, if you have like a degenerate observable, then there's like a variety of states that'll give you the same measurement. So that's not exactly related to the metric, but I'm just saying, like, I think that's how he's using degenerate here. It's that there's actually, like, it's not unique.
It probably was somewhere in chapter 13 when he talked about those, I forgot, like square forms, like bilinear forms, yeah, like bilinear forms. And there should be it somewhere. Like maybe yeah, he talked about positive definiteness here. Yeah, maybe we can just Google it.
319, page 319.
What?
At the bottom of page 319, I think is where.
318?
319.
319. So somewhere here?
Yeah, the end of that paragraph and then going on to the next page.
Yeah, when G is not positive definite, the argument is basically the same, but now the geodesics do not minimize the integral, being what is called stationary, like optimal here. Yeah, but nothing about like degenerate thing. So he just talks like if metric is not positive definite, then this integral, like the length, abstract length here, or time, like proper time in our case, it kind of not. It could be also maximized, like just not minimized in all situations, but sometimes it could be maximized. So it kind of like we will have what is called like extremum situation or stationary situation for geodesics. But probably we'll talk about this in terms of something like principle of least action later. So yeah, and maybe also we will have like more information about this in the next chapter, like chapter 19, for example, where we will talk about general relativity, and he will kind of address this overall process of inducing this connection for the Minkowskian spacetime. Or actually, I can just try to find something here. So degenerate mathematics. degenerate binomial form. It has a non-trivial, so it's degenerate, okay, non-trivial kernel. There exists some non-zero x in V such that, so basically degenerate matrix kinda like collapses in some sense, like d values for some space in V, something like that. So if you have some non-zero vector in V for which you will obtain this for all y's, then it will be called like degenerate. But probably we kind of I need like more time to understand what does it mean in like physical frame. Non-singular. You maybe remember we have seen something like singular linear operation operators or like singular matrices, right? When they kind of collapse the spaces to subspaces.
Right, and that's sort of what Joe was referring to earlier.
Yes. So and basically it's something.
I'll look into it this week. I'll read more about it. We don't have to keep talking about it right now.
Yeah, so it seems that he's speaking about this thing, like when you have some degeneracy in the matrix, when it kind of probably like compresses this space-time somehow. So it's kind of should provide the unique values for every point in space-time or something like that, or pairs of points because of the, like, bilinearities are. Yeah. So maybe.
I asked my next question. I just wanted to open it up to see if anyone else had something that they wanted to address from the chapter.
Yeah. I will take a look at the Discord maybe.
Okay, well then I want to go back to when we were talking about the train problem and how it relates to throwing out the notion of absolute time. Because I'm not sure that this example with the train problem does for us what it was being claimed to do for us. And if it does, then that means I'm misunderstanding something about it. So if we could go back to that and talk more about that. So the idea here, sort of setting the scene, is that we want to adopt the idea of an absolute speed of light c. And then in order to do that, we are going to have to throw out the idea of there being absolute time. Right? That's what we're discussing, right?
Yes, exactly.
And so the question that we're trying to answer is, why does fixing C require us to throw out the idea of absolute time?
Right. So I attempted to illustrate this using a paradox. And the paradox here was that simultaneous events for someone on the train would not be simultaneous events for someone on the station.
But with the tools that we have right now, as of 17.8, what is the justification for that claim?
Okay. Well, yeah. So that's a good question. We're going to need to actually draw out the distances and stuff. So, like, say the train has length d, right? Then the person's standing halfway in between it, so they're both at like d over 2.
Wait, I'm going to write this down on a whiteboard so that I'm drawing it out. All right, yeah, we got a train. Person's in the middle.
Yeah, let's say the train is moving toward the right, and it's got some really high speed, like close to c.
Yep.
And then the sort of layout for the problem is that at the moment that the center of the train passes the center of the platform, a light flashes on either end of the train.
Yep.
So, for the person who's within the train car, you know, there's no experiments that they could do to determine that they're moving.
Right.
And so because of this, you know, and also because the lights are equidistant from them, if we assert that the speed of light is fixed, then the person on the train will receive them in, you know, a time that's like what is it, D over C?
Yep.
Or I guess it would be D over 2C.
Yeah, because of this center.
D over 2, C.
So now, for the person who is who's standing on the platform, let's see. Here, actually, give me a second to pull this up. I think I have a good document that's actually that works this out.
Yeah, meanwhile...
my main question is about the, in this framework that we've got with the tools that we have right now, what is the justification for saying that the person on the platform isn't going to see them, isn't going to think that they're simultaneous?
Yeah, this is a great question, and it really does get to the core of it.